Hello and good morning for everybody. I think this is a beautiful day for having a conference. It's cold outside at last. And I will speak about enhanced sequence modeling with deep learning. Before I get started, I would like to ask you to raise your hands if you ever heard of deep learning, I suppose, yes? And if you ever made an example, a hello world of deep learning. Okay, and if you had a project in deep learning. Okay, thank you very much. So some words about us. I came from the Budapest University of Technology and Economics, from the Smart Lab, from the Department of Telecommunications and Media Informatics. We are about 20 employees there, about postdocs, PhD students, and also MSc students. Regarding our deep learning research, we are into fundamental research, including deep learning, reinforcement learning, and then the HTMs, the hierarchical temporal memories. We are generally making research on sequence and time series modeling, and also speech technologies as the application of these, and NLPs. Regarding deep learning education, we have project labs, thesis, and PhD students. We have an elective class of deep learning with 80 seats in the next semester, and we are also organizing deep learning workshops and meetups in the framework of NVIDIA Deep Learning Institute. And we are also making deep learning trainings and developments for companies. Some words about me. I'm an employee of Smart Lab, and generally I am responsible for the deep learning research and education in Smart Lab. I'm a certified instructor and a university ambassador of NVIDIA Deep Learning Institute, and my main interests are signal processing, time series modeling, and I'm doing machine and deep learning since 2007. So let's get started, and first of all I would like to make clear what is the connection between sequential data, temporal data, and time series. So in case of sequential data, the order of the data matters, but the timestamp is irrelevant. In case of temporal data, we also have some timestamps, so how the data is coming is important. But in case of time series, we have more constraints. In case of time series, the difference between the timestamps is fixed. So we have the same time lengths between the sampling points. To have some examples, the DNA sequences are typical sequential data, or the text of any book is a sequential data. And also, a painting could be a sequential data if you think about the missing parts, and if you take into account in the horizontal and vertical axis the sequence of pixels, then this is also a sequential data. In the temporal data and time series, for example, we have these classic data sets of sunspots, but maybe we would like to model financial time series, which is one of the hardest one. Or in case of consumers, and we would like to model the consumer's behavior, it's also temporal data. And if you consider the movement of objects on videos, it is also a time series or temporal data. Modeling sequential data, the main challenges are the following. First one is to model correlations. The correlation can occur in the sequence, or if we have a multidimensional input, then between the multidimensional inputs, we are looking for correlations. Also, we would like to model multiscale events. If you think about some texts, for example, I like chocolate, not, then the I like chocolate is a much longer sequence than the not, but the meaning of these sequences are really important. So it is like a multiscale event. Or if you think about, for example, financial time series, there are always a long-term dependency and a short-term. For example, if you have some financial problems, then we have to model these multiscale events also. And the third main challenge is to increase the receptive field. That means that how many samples we are considering when we are making a prediction or a classification. And today we will talk about this topic. So let's model some sequential data. And if we approach this problem in the classical programming way, then we know that we have a data feed that is coming, and we are writing rules. We have experts, they define the rules, and then we write these rules in an if, else, then, or a switch case manner. And then we have total control about our algorithm. We can describe why does it do what it does, the answers, why we can describe these answers. But lately, we recognize, the scientific field recognized that maybe it is better to make machine learning as we have a lot of data and maybe we can have some better approach. And we all know that machine learning is about, in case of supervised learning, that we have data and we have answers and we feed it with some machine learning algorithm, and then the machine learning creates the rules, and sometimes we can describe these rules, but most of the time this behaves as a gray box or a black box, so we don't know why did it decide to have some rules. So, and as I saw a lot of you, or about all of you heard of deep learning, and the question is if we go to sequential data or time series modeling, is deep learning the key? So generally, the basic definition of deep learning, if you go to Wikipedia, it says something like deep learning is a part of a broader family of machine learning methods based on learning data representations. And this is the most important part if we compare deep learning with other machine learning methods, because in an ideal case, when we have an end-to-end deep learning system, the feature engineering part should be much smaller than in classical machine learning methods, and the end-to-end deep learning system should learn the data representations and make this the modeling step and the feature engineering part in one step, and this enables us to make better predictions, preferably. In practice, we refer with deep learning to deep neural networks, and we all know that neural networks exist for a long time. And what's new now? We have some new algorithms. We have a lot of data and GPUs, of course, that we can process this data. Usually, I like to add two more things that what's new now. The entry level is much lower. If you go to the internet and you look for some tutorials or online courses, in some weeks you can learn to make basic deep learning applications. Of course, for more enhanced deep learning applications, you have to make a lot of you have to have a lot of practice to do it in a better way. And also, we have an open source research society. So all the results are shared among the research society, or most of the results. These big companies releases their codes. A lot of data are released. Of course, a lot of data are not released. And for example, in the last weeks, the Nature journal announced to have a machine learning journal which is intended to be not free, and there were a big boycott among the machine learning research community that it is not a good way to make research accessible. So about neural networks, if just to brush up our knowledge, it's like we have some inputs, we get the weighted sum of this input, and then we have some nonlinear function that could be as simple as a rectifier function that is 0 before the argument is 0, and it is the argument itself if it is higher than 0. And then we arrange these neurons into layers, and we initialize these weights randomly with some normal distributions. In case of a supervised learning, we put the input samples to the input of the neural network, and then we feed these inputs. We calculate the weighted sum in all layers with the nonlinear function, and then we will have some unreasonable output. But we have the output labels, and then we can compute some errors on the output. And then with the so-called backpropagation algorithm, that is a really old algorithm, we fine-tune the weights to lower this error. And as we feed more and more samples to this network, it starts to learn the data itself, to model the data itself, what we would like. So the learning itself is the fine-tuning of the weights, and when we are done with learning, the knowledge is included in the weights. So let's go to how can we model context dependency in sequences. If we would like to apply such a feed-forward neural network, the approach would be like we would like to model the word hello, then we feed an age, and then we with the network, and we would like to have an E at the output. Then we have an E in the input, and we would like to have an L at the output. Then we have an L input and L output, and L input, O output. Of course, we see that here are some problems to make the same output with different inputs, or have different outputs with the same input. So this is not a good approach, and for that one, the recurrent neural networks are the solutions. The solution when we have some recurrent connection in the network, and when we unfold this network, we can feed the whole sequence with the network, the HELL, and then we would like to have the ELLO output, so we just shift the sequence with 1. To have some more detailed descriptions, so we have an inner state in case of RNNS, and if we use the nonlinear function, the rectified linear unit, then this network looks like that we have the input, the X, we multiply it with some matrix, and then we add the inner state with the W, that is a so-called shared weight, and then the output we have, in this case, some classification with the softmax function. We unfold this network, and then with a given number of state, we represent this recurrence, and then we feed our sequence to the input, we multiply it with the U matrix, and then between the given states, we have this W, which is a shared weight. So when we are making backpropagation, we calculate the gradients and average over the W, and this way it can learn general things about the sequential data, and then we have, of course, also a sequence at the output. The problem with this one, if we have many layers, many time steps, then it is represented in many layers when we are unfolding, and when we are feeding back the gradient, it will vanish. We call this the vanishing gradient problem. So it is hard, or let's say impossible, to train such a network. And the receptive field is very small. It is few tenths of previous samples. This one was solved in 1998, I think, by the LSTM. Of course, we needed more data and GPUs with some tricks that we have for 3 gates, the input gate, the forget gate, and output gate, that controls which data we should feed with the network, which data should we forget, and which data should we output for the next time step. And these features are learned from the data. And of course, we have a memory cell inside this data. And when we have such an LSTM cell, we can arrange it in the same manner as in case of the recurrent solution. And for example, this is one of the simplest applications when we have a sequence of data, and then we would like to make some predictions or classifications at the end. One of the most basic example of LSTM is modeling text, like you have some input, for example, 40 characters, and you would like to predict the next character. This is a Hungarian text that was trained on the Dostoevsky Sin and Punishment book. And you can see that, of course, it makes no sense, this text. For example, mi a rábólint, hátrafordult még mi, rikor intebb az is ugyan nap tanú előtt, etc. But you can see that it learned, for example, that we have paragraphs, we have capital letters, we have punctuations, we have these common terms that are in the book. Okay, let's go further. The LSTMs has few tens to few hundreds of receptive field, but the main problem with LSTMs that they are really slow to train. And for example, we have to wait days or even weeks on high-performance GPUs. And for that one, in the last years, the so-called convolutional neural nets are getting more and more familiar in sequence modeling. And in this case, if we model sequential or temporal data, usually we apply one-dimensional causal convolution. In case of causal convolution, we have the input, in this case a multidimensional input. Each line refers to one dimension. And then we slide a so-called filter over these inputs. And in the next, we have weights also connected to this filter. And then we calculate to the next layer these weights as we slide it over the input. We calculate it for all the slices of the next layer. And as these weights are initialized randomly, different features will be learned from these input sequences. If we stack these layers onto each other, you can see that in this case we have 3 hidden layers. And then with one output, we can have information from 1, 2, 3, 4, 5 inputs. If we stack more layers, let's imagine 50 layers, we have a larger receptive field at the input. Training CNNs is faster than training LSTMs, and the receptive field in case of causal convolution is almost the same than in case of LSTMs. But the problem here is that the hyperparameter space, so the settings that how the network would look like, is very large. And in this case, not the training itself, but the hyperparameter search takes a lot of time. Currently, the state-of-the-art solution in terms of sequential modeling is the one-dimensional dilated convolution that is very similar to the previous one, but in this case, in the hidden layers, we have some dilatations. So we just consider every second, every fourth, every eighth, and so on neurons. And this way, with almost the same number of weights, we can have a much larger receptive field. So in this case, you can see that with one output, with 3 hidden layers, we can have a much larger receptive field than in the previous solution. With dilated convolution, we can have few thousands of receptive field lengths. And the problem is still that the hyperparameter space is quite large, and we have to make a lot of hyperparameter optimization. For hyperparameter optimization, of course, we need data and GPUs. And the problem is usually, as always, that we have to make hyperparameter optimization for different data sets always. So usually we have to remake it to have the most highest accuracy or most lowest error function. OK, so let's go for some applications. We have some spin-off company that is called SoleCall, and this company, what it does, it is develops a security application for deaf people, and it's like that it detects that the person who has some problems, he tramps 3 times like this, and then the mobile phone of the user calls the police, for example, or makes some emergency calls to some prepared numbers, and then help may come. To detect such a tree tramp, it's much more challenging than it sounds, because we have to have a really low misclassification. So if you go around with different kind of mobile phones, it is not good if it alerts always. And to solve this, we applied one-dimensional convolution. On the input, we had a 7-dimensional input. These are the sensory data coming from the mobile phone, for example, the accelerometer data and the orientation sensor. We made a really long hyperparameter optimization. It took about half a year on 10 GPUs. 10 high-performance GPUs. Of course, we made a lot of fine-tuning. And the output is, in this case, a binary classification if there were 3 tramps or not. And we achieved a really nice accuracy. Here are some network designs, a larger one with 600,000 parameters, and the second one is 300,000 parameters. So it takes So in high-end mobile phones, we can apply this. In lower-end mobile phones, we apply the smaller one. Here you will see some short videos about how does it work. Here on the left side, you see the probability if there was 3 tremors detected, and this guy will make, he will try to trick the mobile phone. Okay, he just trembled 3 times here, so you can see that there is a signal. And it also works if you put it in your bag. So even if it is not in your pocket, the mobile phone, in this case, he has his phone in his pocket. And now he puts it into a bag. And you see he is moving it, but the probability of having an emergency call, it is 0. He is running, there is no problem, and when he will tremble 3 times, there will be some signals. So another application is the so-called WaveNet that was invented by Google DeepMind in September 2016. The idea came from the Pixel CNN and Pixel RNN, and it is a novel approach to make text-to-speech synthesis. It models the raw audio waveform. So from previous 4,000 to 8,000 samples, we predict the next one. So it's like we predict the next one, then we slide the window with 1, and then we always again predict the next one. We made modifications to this WaveNet because the Google WaveNet was trained on the Google TPUs for weeks. Of course, we don't have these resources. We made some modifications, and now we have 1.2 million parameters in our WaveNet structure. We trained, here you can see the training. It takes about 3 weeks to train such a model on 20 hours of speech database. On high-end Titan XP GPUs. And here you can hear some examples with our WaveNet. Of course, these examples were not included in the training data set.
Személyi vonati impulszvegyős Szolnok-Kisú szállásra 15 óra 14-kor, 15 perc múlva Ausztalikrajnányról. Felhívási megkapaszkodott, új egyet, majd lélegzetet vesz, és ismétel elő.
Currently, this is the state-of-the-art solution in text-to-speech synthesis. And in Google Duplex, they are using WaveNet, or in call centers, railway stations. We have our system deployed in Déli pályaudvar, Keleti pályaudvar, Székesfehérvár, and a lot of places. Currently, it is running on another TTS system, but we are planning to apply this one. So the summary of today's presentation, that deep learning is really effective in modeling sequential and temporal data. The baseline approach is to have LSTMs with a lot of training times, or causal convolutions with hyperparameter optimization, and in this case, the receptive field is few hundreds, or we can apply dilated convolution to increase this receptive field to few thousands. But hyperopt is still necessary. So if you have any questions, I'm happy to answer, or you can send me some emails. We are open to collaborations, and thank you for your attention.
I would have a question related to this very last topic. Did I understand well that you developed this system in order to so what kind of information you get for these samples at the end? What you used for the Keleti the railway stations and others. So you have some data from the trains, or you have something, or it's already set when you have this.
No, our part is only to make the text-to-speech synthesis and that part, because a lot of time the timetable changes. You have new station names, new train names, and in the I don't know, 10 years ago, they always had to ask the lady to come and make recordings. And when you are making such a system for a long term, then the voice of the lady changes. Or if, for example, she goes abroad and they have to change the voice, then it is a big challenging task because they have to make all the recordings again with a new person, and if that person goes away again, then they have problems. So that is the reason why they need text-to-speech on the railway stations. Currently we apply some other methods, but it is very restricted and it is not as flexible as the WaveNet approach. And right now we are working on applying this WaveNet to the railway stations also, but it is a general approach, so it's not only for railway stations.
Okay, thank you very much. Any further questions? Oh, at the back.
Yeah, I mean, a little bit in the back. Do you use FPGAs for execution, like it is possible with TensorFlow and OpenCL, and why not?
Sorry, could you repeat it a little bit louder?
Yeah. Do you use FPGAs, like it is possible with OpenCL and TensorFlow?
No, we are using GPUs right now. Generally, we are an NVIDIA lab, and we have NVIDIA GPUs. We didn't make any experiments yet with FPGAs, but as far as I know, right now the tools of NVIDIA is much more mature in terms of deep learning. For example, the QDNN is optimized for making these convolutional steps on the Volta cores, and it is really much faster, but it would be nice to have some experiments on FPGAs and OpenCL also, yes. But generally, we are using TensorFlow, yes.
Thank you. Come talk to us here in the back later.
Okay.
Thank you. Further question? No. Okay. If not, let's thanks Bálint again.
Thank you.